Solid, liquid, or gaseous, we only know three states in appearance, except that it can be superfluid and climb walls defying gravity. Transform into liquid crystals, into black water ice that burns and conducts electricity, into quartz soup, into Bose-Einstein condensate, and even into time crystal. Matter is everywhere, resisting under our touch, composing our bodies and landscapes. It is the wood, rock, falling rain, and smoke, like the ground beneath us. The glass of the screen through which you are looking at me and the air you are breathing. But all the examples I just mentioned and which are familiar to you are limited to the states that matter can take, under normal conditions on Earth where it always behaves with a certain restraint. But when it is heated to blindness, crushed, ground in the heart of dying stars, or frozen, cooled to silence, matter begins to change its face to wear other masks. And suddenly, the one we thought we knew adopts extravagant forms and acquires literally hallucinatory properties. As you've understood today, we're going to dive into what matter can become when it's pushed to its very limits. By colossal pressures and temperatures that are hard to imagine, whether it's produced by the all-powerful machines in our laboratories or by natural phenomena. That being said, let's get back to our adventure by getting straight to the point. Starting with the first state of matter, the so-called solid state, where it is frozen and which will allow us to lay some foundations. Solids have this particularity that they do not change shape when left alone, and many resist when we try to deform them. They have a defined volume that they maintain under normal conditions when we do not try to burn them or crush them. This behavior results from the way matter is arranged in the infinitely small. If you could observe the structuring of atoms in a solid, you would see them closely linked to each other, like the stones of a building. Sometimes this architecture of immobility takes the form of a crystalline order. Other times, as in glass, it's an apparent chaos frozen in disorder. But each time the atoms are forced to stay in their place. Rigidified together, they only vibrate around their equilibrium position, never straying from their neighbors. Because the forces that unite them are so powerful that they cannot move freely. Solids have a stable shape and a defined volume, and when they collide, they do not mix. Liquids behave differently because the atoms within them are less strongly bound to each other. This allows the matter to dance freely, the atoms to bypass each other, to slide, to move, while maintaining a certain cohesion. And in this state, which is that of lava, oceans, and sand, matter flows, always taking the shape of its container. Finally, in a gas, whether it is ambient air or water vapor evolving in a spiral above your coffee, the atoms, the molecules move so quickly that they become unable to bind and continuously disperse, trying to occupy all the space. Therefore, matter in gaseous form has neither shape nor defined volume. And in the infinitely small, each atom, each molecule lives its own life, bounces, escapes, forgets itself in a great freedom of movement. Surprisingly, none of these three states that are familiar to us and of which our bodies are made is the form predominantly taken by matter. In the universe, where more than 99% of atoms are in the form of plasma, sometimes called the fourth state, it is this form of matter that makes up almost all of the stars in the universe. To understand plasma formation, let's go back. A solid's microscopic image. If we heat it enough, then the atomic bonds that keep the material rigid will eventually weaken, to the point of allowing the atoms to start moving and thus form a liquid. And if we raise the thermometer even further, even the most tenacious bonds will break, and the atoms start to whirl freely and form a gas. In short, solids can become liquids, and liquids can turn into gases. Now, if we heat a gas to temperatures of the order of several thousand degrees, the electrons orbiting around the nuclei of the atoms that make it up will eventually be torn from them. And we're going to end up with a soup made up of electrons and atomic nuclei unable to bind as the temperatures are so high. This mixture of charged particles, which have the strange property of behaving like a fluid capable of conducting electricity and producing magnetic fields, is called a plasma. Although plasma is the most common state of matter in the universe, where it is found in incandescent form in stars as in interstellar gas, it is extremely rare on Earth. On our planet, it only forms momentarily around the edges of lightning or in the heart of nuclear reactors. And we can admire its presence in the northern lights. Just like in the lamps to which this strange state of matter has given its name, the plasma lamps. Inside these, plasma is temporarily formed, not by heating the gas trapped in the lamp to extremely high temperatures, but by circulating an intense electric current through it, which, as it passes, peels off the atoms whose electrons are torn from the nuclei. Solid, liquid, gas, plasma. When discussing states of matter, we usually stop there. But these four basic states are just the faces of matter that are familiar to us and that we can find or observe in the natural state around us. But other masks exist, and to encounter them, we can start by simply being interested in the surprising behavior that matter adopts when we are in balance, at the border between two states. This is the case with liquid crystals, which are neither fluid nor frozen, but an intermediate form of matter that refuses to choose between solid and liquid, and whose atoms are aligned and structured like those of crystals, while accepting to move. This strangeness, you have it at home right now, because liquid crystals are the basis of liquid crystal display screens, in which we submit this material to an electric field to rotate its atoms and thus change its apparent color by modifying the path of the light that passes through it. In fact, it was the advent of this technology that sounded the death knell for plasma screens. These fascinating materials that are liquid crystals are not only found in our screens, they are also found in living beings. Inside peacock feathers or butterfly wings, there are proteins from the keratin family which form liquid crystalline arrangements responsible for certain iridescent color effects. There are even liquid crystals currently in your cells. Because lipid layers, which form the cell membranes of both plants and animals, indeed adopt often phases of liquid crystals, whose structure, both rigid and flexible, allows for lateral flow. Now, if we add to the equation the increase in temperature and pressure, we get absolutely baffling things, such as supercritical fluids that form at the boundary between liquid and gas, and that we find in the natural state on the surface of our planet. On Venus, where the average ground temperature is about 465 degrees and the atmospheric pressure is 92 times greater than that of our planet, the carbon dioxide present in the air no longer behaves like a gas, but like a supercritical fluid that shares the properties of liquids and gases at the same time. That is, they infiltrate and diffuse everywhere extremely quickly, while being able to dissolve the elements they encounter with the frightening efficiency of a liquid. This strange state of supercritical fluid is observed for all elements, as long as you are able to heat them while keeping them under sufficiently strong pressure. Thus, if you heat water vapor to more than 374 degrees Celsius, while compressing it under 221 bars of pressure, you also get a supercritical fluid. Now, if I tell you about a black ice that burns the skin and conducts electricity, you would say that I've lost my mind. Yet, the existence of this matter was predicted by our theories long before we were able to manufacture it in small quantities in our laboratories, at the end of the 2010s. On the surface of our planet, water ice always has the same crystalline structure at the microscopic level. The atoms are generally arranged in an ordered pattern that repeats itself infinitely in the crystal. But if we increase the temperature and pressure conditions, this structure will profoundly change. Thus, we know about 15 different atomic structures for water ice alone, and each of them has atypical properties. Those called superionic ices, also known as ice-8s, and are black in appearance and hotter than lava. Just like Ice-10, whose structure only appears at pressures 600,000 times greater than those of Earth's atmosphere. Ice-10 therefore only forms on our planet during laboratory experiments conducted using diamond anvil presses. But it probably exists in large quantities in the bowels of icy giant planets like Uranus or Neptune, where the presence of these conductive crystalline structures could help explain the strange characteristics of the magnetic fields of icy planets. Thus, there is surely more solid water in our solar system in this exotic form, which only appears under colossal pressures, than in the classic forms we know. Another example of materials whose behavior is mind-bending. At staggering pressures, on the order of 6 million times those of our atmosphere. Oxygen, long solid at such pressures, also ceases to be insulating to become metallic and sees its electrical resistance disappear. Perhaps even more fantastic than these exotic states related to high pressures are those discovered by exploring the behavior of matter at extremely low temperatures. If you take helium and cool it down to less than 171 degrees Celsius, or just 2.15 K from absolute zero, then the helium will become liquid but also transform into a superfluid. In this unique state in the world, if the liquid helium is in a ceramic container, it starts to escape by passing through the bottom, flowing between the atoms through the matter. If the container is made of glass, then the amorphous arrangement of atoms prevents the helium from passing through. And it will then escape on its own from the container and climb up the sides by capillarity, as these images show. In superfluid form, liquid helium even has zero viscosity. So much so that if you impart a motion in its container, it will continue to spin, never slowing down for eternity. Or at least as long as you can keep the experiment under minus 171 degrees Celsius. At such temperatures, the container's material, superglue, glass, or Velcro, is irrelevant. Liquid helium has no friction with any material in the known universe nor with itself. Perhaps even more fabulous is cooling particles down to staggering temperatures, on the order of a few millionths of a degree, above absolute zero. We discovered the existence of condensates, manifestations of matter in the infinitely cold, which are so bizarre that they are sometimes considered a fifth state. When a grouping of a few hundred to millions of atoms reaches the lowest possible energy configuration, something fabulous happens. The particles of the mixture cease to have individual behavior and become one. They become a condensate in which the particles that were there previously have merged their wave functions to collectively adopt the same quantum state and together form a giant and unique wave function. All the particles that participated in giving birth to the condensate have then lost their individual identity. They have, in a way, superimposed and synchronized, so much so that it has become impossible to distinguish them from one another. They then behave only in a coherent and collective manner. I won't dwell too much on the subject. Their wave functions are already doing enough of that. Let's now take a 180-degree turn to focus on the forms of matter that come into being, at high energies in the realm of the infinitely hot and sometimes compressed. Starting with what is called degenerate matter. This forms at the center of dying stars, when the nuclear reactions that make them shine stop. And the considerable mass of the dying star tends to make it collapse in on itself. On an atomic scale, electrons, which refuse to occupy the same quantum state as their neighbors, manage to withstand the star's collapse by refusing to give up their place. And then they form an exotic matter that is said to be degenerate, in which the particles are so compacted that a cubic centimeter of this degenerate matter weighs nearly 10 tons. Strangely, in this matter with staggering densities, which make up the stars we call white dwarfs, the electrons circulate almost freely between the atomic nuclei, compressed at speeds close to that of light. And it's the presence of this degenerate electron gas, almost perfect heat conductor, that allows to evacuate from the inside of these small dead stars, and in the form of light, the staggering amount of heat stored during the collapse. This means that these stars, although already extinguished in the sense that no more nuclear fusion reactions are taking place in them, still shine faintly long after their death. Another surprising element with this degenerate matter is the size it gives to objects. Normally, if you take something solid or liquid, a planet or an ocean, and you add matter to it, your planet, your ocean will gain in volume, will become larger. But in a star made of degenerate matter, it's the opposite. The more massive a white dwarf is, the smaller it is. In other words, the heavier the star is, the more its mass fits into a narrow volume. The reason is that the more massive a white dwarf is, the more intense its gravity is. And the more the electrons are forced to squeeze together to get closer to resist the collapse, the more the volume of the degenerate matter star decreases. Thus, a white dwarf, heavy as half a sun, is practically the size of the Earth, while another white dwarf, 3 times heavier than our Sun, will be smaller than the Moon. And it's gravity that will allow us to encounter a type of matter even more compacted than degenerate matter, and sharing with it the disputed title of sixth state, and what we call neutronium. Neutronium forms in the universe when an extremely massive star collapses under its own weight, and the electrons that make it up are unable to resist the force of gravity, and can no longer maintain matter in a degenerate form. A neutronium ball is then formed, a star nearly 1,000 times smaller than a white dwarf, and in which is compacted within a diameter of about 10 kilometers, more than 1.4 times the mass of our Sun. Neutronium is almost exclusively made up of neutrons, having formed from protons and electrons, which, crushed by the force of gravity, were forced to come closer, to the point of merging. This form of matter, where the atomic elements are so close together that the volume of a grain of rice weighs as much as 100 Eiffel Towers combined, is today the densest matter in the known universe. It's possible that in the depths of these stars, matter denser than neutronium may exist. We know that we are touching a limit here because by further increasing the density of neutronium, we quickly reach a point of no return, where the curvature of space-time gives birth to a black hole. Finally, if we release the pressure and continue to raise the temperatures even further, we end up encountering the most primitive and fundamental form of known matter, which is sometimes considered its seventh state and is called Quark-Gluon plasma. Unlike neutronium, this matter is relatively well known to physicists who manage to recreate it momentarily in particle accelerators, by propelling gold or lead nuclei against each other at speeds close to that of light. And in doing so, they locally heat the matter above the terrifying temperature of Hagedorn, which, at 1,700 billion degrees, marks the limit beyond which protons and neutrons, the so-called hadronic matter, break down into smaller elements to take the form of a soup of quark and gluon plasma. And in doing so, the temperature of Hagedorn can be considered as the liquefaction point of the constituents of ordinary matter. Thus, unlike the plasma of ordinary matter found in the Sun and which flows like a gas, a quark-gluon plasma flows in a way, like a liquid in which the fundamental building blocks of matter move freely in an ocean of gluons and force fields. This strange state of plasma was the first temporary state of matter during the early moments of our universe. Because in the seconds following the Big Bang, the temperatures were so high that matter was just a fog of quarks and gluons. From this point of view, it's amusing to think that the fundamental elements that make up all of us have momentarily passed through this state. Now, consider this. If a quark-gluon plasma behaves like a liquid, that means it can freeze. For that, it simply needs its temperature to drop below that of Hagedorn, the liquefaction point deconstituting ordinary matter. From this point of view, the nuclei of atoms are crystallized quark-gluon plasma. In other words, the matter that constitutes us today is nothing more than primordial plasma that has solidified. In short, it's hard to say exactly how many different states of matter there are in the universe. If we consider that a state of matter is a set of emergent behaviors whose new properties distinguish it from all others known, we have already identified quite a few. On the sole Wikipedia page about them, we count no less than 100, knowing that there are surely many that have not yet been discovered. Physicists, who often have a way with words, have given them names that are invitations to travel, such as photonic matter, Rydberg molecules, quantum fog droplets, or even the delightful colored glass condensates. A type of matter whose unique properties can only be observed in atomic nuclei moving at a speed close to that of light. But my favorite type of matter is by far the baffling time crystals, in which matter takes the form of a crystal, whose pattern does not repeat geometrically in space but dynamically in time. Time crystals are a type of matter whose structure oscillates and changes itself at regular intervals. In a time crystal, a dozen atoms in a carefully controlled quantum state and periodically subjected to a laser pulse can respond with a rhythm of their own. Offset. This kind of matter, whose surprising emergent property is to have an integrated clock, is a non-equilibrium state that repeats over time, without net energy consumption. It's not just weird, there's no known equivalent, it's fundamentally new and awesome. Especially since the ultra-low oscillations of time crystals could perhaps one day be used to store or transfer quantum information. In short, matter was definitely a comedian. And the three faces that are familiar to us are just a tiny part of an iceberg made of hot ice, incandescent plasma, superfluids, or other exotic arrangements, which naturally form in the cold of space, in the bowels of stars, or in very distant pasts. And each of these states, these different masks that matter spontaneously adopts when subjected to particular conditions, allows us to learn more about the laws of nature that, behind the scenes, pull the strings of these parades and authorize or not the existence of these different disguises. The next time you contemplate an ice cube melting or a liquid crystal display smartphone screen, remember that all this is only a temporary costume and what we call matter is just a temporary role. A fleeting mass that can transform, depending on temperature and pressure conditions. And that, in this theater, one of these Harlequin costume arrangements has produced humans. Improbable accumulation of matter that began to study itself. A piece of the universe that looks at itself,